go from current slide. And first thing I want to know, any questions from anybody? Okay. If not, where we left off last time was Chapter 8, Work and Energy, and Section 8.3 is the energy part. We had just talked about potential energy. Can someone remind me of what potential energy is?
The work needed to be provided to the position.
Okay, the energy that depends on the position. And do you remember a formula for it? Now they just say E sub P. I like to say E sub, or I like to say GPE because that says it the best. Gravitational potential energy. But they're just saying E sub P, and they're just understanding it to be because of gravity. Okay? So what is that potential energy? Anyone remember? Guess what? It's got to have gravity in it. So there's got to be a G there. M, G, H, where H is the height above the reference level. Now, I can't remember if we talked too much about the reference level before. It seems like we're just getting started in this. So did we mention reference level? I don't recall it. Did we? Okay. If I remember, I was going to be dropping a book on Trish's toes, right? Okay. Now, if I'm holding the book above the table, and that's where I'm going to drop it, this would be the height. Okay? Zero reference level. That's my zero reference, so this would be the energy above the table. But if I moved out here, then the odds are my reference level needs to be there. So you have to first establish your reference level. Now, most other courses I teach from the second floor. And then I go to the window and hold out there, but I'm on the first floor here, so that's about the same height as the floor here. But if we're up on the second floor and I went out there, then the ground may be the reference level. Or sea level may be the reference level. Whatever, and my rule is, whatever as low as the object can go in this particular problem, that should be the reference level. So if it's only can go to the table, use the table. If it can only go to the floor, use the floor. Okay? But whatever is the lowest place it can go, that needs to be the zero reference level. And then the height, H, is measured from that reference level. Okay? So that explains hopefully that. Now, someone remind me of what that G can be. We assume we're on the surface of the Earth. We're not going to go to any other planets or the moon or anywhere else today. Say again? It is acceleration due to gravity, and what's the value of that? Okay, 9.80, the book likes to call. And what units would that be? Meters per second squared. Or, if you're in U.S. customary system, it would be, anyone remember? 32.2. What units? Feet per second squared. Okay? Remember, there's a little more than 3 feet in a meter. A yard is from my nose to the tip of my finger. A meter is from the opposite ear to the tip of the finger. So the meter is a little bit longer. So there's 3 feet in a yard, so there's a little bit more than 3 feet in a meter. So that's why if you multiply 9.8 by 3, you would only get 28 or 29 something, another 29 something. But from a little bit more, you get 32.2. Okay. So there is the formula for gravitational potential energy. Okay. I think we're ready then for example 1. I think I'll go on and erase this one, what I've got here, but remember the formula. We'll be using it. A wrecking ball of mass 200 kilograms. And they told us this was a mass, 200, and they put a bar over that second zero. What does that mean? Say again? Second, significant digits. The 2 is significant, the last 0 is significant, that puts the 1 in the middle significant too. Anything between 2 significant digits is also significant. So a wrecking ball of mass 200 kilograms is poised 4 meters above a concrete platform. So here is the wrecking ball. Okay, there's the wrecking ball, and it's poised. I didn't know wrecking balls were that poised, but that's 2 meters above a concrete platform. Okay? So this is, I'm going to do from the bottom here, this is 2 meters. It's actually 4. I can't read. 200 kilograms, but 4. Well, didn't take. All right, there we did. The height is 4.00 meters above the concrete platform. Okay? Whose top is 2 meters above the ground. So here's the ground down here. So this is 2.00 meters here. The A part of this question says, with respect to the platform here, what is the potential energy of the ball? So we're looking. Oh, there we go. So we're looking for potential energy, which, I'm sorry, they use a different symbol. E sub P, and they're meaning gravitational potential energy, so I'll put the G there to remind you. And what's the formula for gravitational potential energy? Just had it. mgh. What's your mass? 200 kilograms. Perfect unit for mass. Times, what's your G? Yes, because you're using kilograms and meters, you use the SI unit, which is 9.80. What units? Meters per second squared. And what's your height? 4, because you're doing it above the platform. So that would be 4.00 meters. Okay? Now, pretty easy to multiply 2 times 400, that's 800. Multiply that by 9.8, and you get something a little bit less than 7, I can't think today. You get 7,900 something another, right? 7,800, something like that. Someone help me out with the math. 200 times 9.8 times 4. 7,000 what? 840. What units are those? Anyone make a guess? You could use the ones we got here, which is a kilogram meter squared, there's a meter, per second squared, or that can also be represented as a what? 2 other options here. Anyone know what energy is measured in? Say again?
Watts.
No, that's power. Power is energy per unit time. That would be in watts. What would energy be measured in? Say again? Thought someone may have said it. Joule, exactly. You could have also said a Newton meter, because a kilogram meter per second squared is a Newton, and then multiply that by meter and you get a joule. So 7,840 joules. Now, did you round that, or did they have it round? Okay. Now, what if I wanted a smaller number but a bigger unit? What would that be? what would that be? 7.84 what? What unit? Kilojoules. Okay. Now, tell me something. Is that 0, 7,840, is that 0 significant? No, because you only have 3 significant digits here, 3 there, 3 here, so you only count 3, 1, 2, 3. That last 0 is not significant. That's why we do not put the bar over it. You have to have it there. Okay, you have to have it there to hold the place. It's not 784 joules, it's 7,840 joules. So you do need the 0 there to hold the place, but you don't put a bar over it because it's not significant. You can't have more significant digits coming out of a problem than you have going in. Now let's look at the B part. The B part says, yeah, sure. Okay, say this again. Yeah. 5. Okay, if you got a 5, because you have 3 digits here, 3 digits here, and 3 digits for your 9.80, wherever that is, right there. Okay, then you can only count 3. So 1, 2, 3. Look to the right. If that was a 5, then you make this a 5 and drop that to be a 0. Because 45 would round to 50. Okay. Good question. If it was 4, you drop the 4 and just put a 0. You can only have 3 significant digits. You have to have 4 digits because it's in the thousands of joules, but only 3 of them are significant. That last 0 is not. And that's why when you write it as 7.84 kilojoules, you see exactly the significant digits. Good question. All right. Now the B part, any other questions? The B part says, with respect to the ground. Now we've made the ground our 0 reference level. Okay? What is the potential energy of the ball? Ball's in the same place, but you just change your 0 reference level from the top of the concrete platform to the ground. So what is the formula we'd use here? Same as before, E sub P, and this is gravitational potential energy. E sub P is equal to what? That formula? M G H. What's changed here? Mass is still the same, 200 kilograms. G hasn't changed any. You're still on the Earth, 9.80 meters per second squared. But what has changed? The height. And what's the height now? 6, because you're 6 meters above the ground. The 4 plus 2 gives you 6 meters above the ground. That's your new height, 6.00 meters. Okay, you multiply those together. I don't know why it's flashing today so badly. There we go. What does that give you? $392 plus 784, 176 or something like that. Is that it? 11,760. Is that what you said?
Yes.
Okay. 760. What units? Joules again. Okay. Now, what about those digits, say? All right. We only have 3 coming in, but we got 4 coming out. Okay. What is the problem here today?
Tell me if this does anything. Not a thing. This is an old computer. Ah, there it goes. See, as soon as I start talking about it. So what do we do here?
Look at the digits after the 7.
Okay, yes, we count 1, 2, 3 digits. Look to the right. That's a 6. What does that do?
Allows you to round up.
Okay, 11,800 joules. Or written with a smaller number, bigger unit, what would that be? 11.8 kilojoules. Perfect. Perfect. The book doesn't do that last part, but we can. All right. That's how we deal with potential energy. Potential energy, gravitational potential energy, E is equal to mgh. Okay? Now, if that looks a lot like work, it really is. Mg is basically a force times the distance. That's almost the same formula. We just use different letters for it. The same thing, it has the same units. So gravitational potential energy, work, very, very closely related. All right, there is another kind of energy, though, that we deal with, and this one, I won't want to say more, but seem like we do it a lot. That is kinetic energy. Now, what does the word kinetic connote to you? Remember, we had kinetic friction as opposed to static. Moving. See, potential energy was the energy of position, not motion. Kinetic energy is the energy of motion. So it's going to have a different formula. Now, if something is moving, what quantity must it have? If an object is moving, what quantity must it have? Of course, everything has mass, so that's still in there. Velocity, you're absolutely right. If it's moving, it's got a velocity. So the kinetic energy depends on velocity, but in a little bit different way. Here is your formula for kinetic energy. Okay, kinetic energy is due to the mass of the object and the velocity of the moving object, and is given by E sub k, and I like to put ke, they like to write E sub k, and they put a little k, it doesn't really matter, is equal to 1/2 mv squared. There's your mass, there's your velocity. What's different in this one is the velocity is squared. Now, a little bit of a timeout here. A lot of times in physics, when your main variable is squared, it's going to be preceded by something over 2, like the 1/2 here. We'll see some other formulas that are the same way. Most of the time we'll have 1/2. There's 1 or 2 that won't have that, and there are reasons for those exceptions. Most of them will have that. Now, I've seen books try to explain this by it's an average of 2 velocities or something like that. Really what it is, you don't need to know this, it's an integration constant. So you don't need to know that. That's what it is. Anytime you have a 2 up there, you have a 2 in the denominator. Most of the time anyway. Okay? Now, let's take a look and see. 1/2, does that have any units? No, it's just a pure number. How about mass? What would be the unit for mass? Let's use SI. Kilogram. And how about velocity? What would be velocity? Stay in SI. Be a good unit for velocity. Meters per second, absolutely. Distance per time, meters per second. But you're squaring that. So you're squaring not just a number, you're squaring the units as well. So what does this give you? Kilogram, meter squared, per second squared. Guess what that is? A what? A Newton meter, or what's another name for that? A joule, exactly. Same units as work, same units as potential energy. All energy units and work have the same unit. Okay. Now, some things to note about that. Kinetic energy depends on the mass, just like potential energy depends on the mass. Potential energy depends on the height. Okay? Kinetic energy, though, depends on the velocity squared. Now, that's a big difference. Okay? One place that it's a really big difference is when you're driving. Okay? If you're following along a car or a truck or something like this, and you're going, say, pick a speed.
50.
Second?
50.
50 miles per hour. Okay? Let's lower that some and pretend it's only 25. Okay? 25 miles per hour. Okay? The energy you would have would be 1/2 your mass times 25 squared. 25 squared is 625. So that's going to be a pretty big number. Okay? But if you were following along at 60 miles per hour, you've doubled the speed. No, wait, you said 50. Okay. Right? Yeah. 50, you double that speed, and when you square 50, you get 2,500 times your mass times 1/2. My word, you went from 625 to 2,500. You've increased the energy 4 times by just doubling the speed. That happened. Triple the speed, increase the energy by 9 times. So that means if you can safely follow that truck ahead of you at 25 miles per hour, so far behind it, when you get up to 50 miles per hour, you should not double the distance behind it, quadruple the distance behind it to be safe. Most people don't do that on the expressways, and when there's an accident, it's usually a vehicle. Okay? If people are crowded in there going at high rates of speed, no way they're going to be able to stop. And then the destruction's worse. It's a mess. And you'll see that. I drive into work from Birmingham to Bessemer every morning, and so many times, I started to steal your projector cord there, but it wouldn't work, so I put it back.
Okay. I keep putting the computer bag.
And so I'll drive in, and just about not always, so many days, there will be backed up traffic coming in because there's been a fender bender somewhere there, people going too fast, not able to stop, and crashing into the back of somebody or sides. And some of those look pretty rugged to me. All right. So there is your kinetic energy formula. All right. Now, they love these illustrations of pile drivers. And what I'm going to do is jump a little bit ahead because they don't have the figure here, but you sure don't want to see me try to draw it. So this is coming up later, but this is the example of the pile driver. There's an actual picture in the book, not a diagram, but it's the same general thing. Okay? What you do, you're trying to drive this pile into the ground. Okay? They do this anytime they're doing a foundation for buildings, for roads, for bridges. They drive the piles into the ground. What they do, they have a sort of a shaft here. Then they have a heavy weight that they lift up to the top of the shaft and then release it. And when it releases, it falls down at a pretty high rate of speed because it's pretty heavy and pounds the pile into the ground. Okay? Now, what you're dealing with there is when this guy, the operator here, picks up the POW and raises it to this height, he is doing work on the POW. He's lifting the POW. mgh. That's the work he gave. Well, that work is now potential energy. mgh. Okay? That's how much potential energy it has from this zero reference level. So when he releases it, it immediately starts falling, and it picks up speed as it goes. You may not realize that, but it does. And by the time it reaches the bottom, it's going at its maximum speed. Because right when it hits, then all that kinetic energy from the velocity of it now changes to drive that into the ground. So you're giving it gravitational potential energy, releasing it, it gets kinetic energy, and then that's what does the work driving this into the ground. So that's what they're getting at here. And they give you that formula on the next page. Okay? And this isn't quite what they're talking about here, but it's pretty close. Let me get my pen set up again. Okay, right here at the bottom, after you release it, it has kinetic energy of 1/2. What was that kinetic energy formula again? Oh, how soon we forget. Mass times velocity squared. Okay, whatever its speed is right there at the bottom. Now I'm all tangled up in my wire. Okay, that's the speed. That's the energy it has right before it hits that. When it hits it with a force that drives it down some distance. This is your distance S. And that's your formula for how the pile driver works. The energy it has, kinetic energy it has right when it hits, that's equal to the force times the displacement that it drives it into the ground. Okay. So I'm going to still use this one even though it's not meant to be used in this way. I'm going to erase this ink for now. And a pile driver with a mass of 10,000 kilograms. So the mass of this pile driver is 10,000 kilograms. Now folks, that's pretty heavy. Okay? That would be equivalent to what they call 10 metric tons, which would be a bit more than our English tons. That's a lot of mass, a huge amount of mass. Okay? So 10,000 kilograms strikes the POW with a velocity of 10 meters per second. So V sub S, I'm going to say the velocity of striking is 10 meters per second. Okay? It's 10.0 meters per second. Because this is 3 significant digits, that's 3 significant digits. Okay? The A part of this question says, what is the kinetic energy of the driver as it strikes the POW when it's right here? What's the E sub K? Say again, what's the formula? 1/2 m v squared. Okay, so that would be 1/2. And what was that mass? 10,000 kilograms times, and what was the velocity? 10.0, what units? Meters per second. But what are we going to do to that? Square it. Okay? Now I'm going to do the first part. It's okay to do this ahead of time. Do 2 into 10,000, then that gives us 5,000. Okay? Well, actually, the second zero becomes significant now. Where's my eraser now that I need it? There it is. Okay. Okay. 5,000 kilograms still. And what's 10 squared? Anybody? Second? 100. 100. And what units? Meters squared per second squared. You don't just square the number, you square the units as well. Now notice I didn't put a .0. Why? because 3 significant digits. The last 0 is significant. I don't need a .0. That would give it 4 significant digits. So I do 5,000 times 100. That would be 5,000,000 kilogram meter square per second square. What unit's that? Joules. And how many significants do I have? Howdy. Yes. Yes, sir. Okay. Okay. Excuse me just a minute. Let me put this on pause. Yes. Oh, I see. Okay. All right. Let me put this in my book there. Okay. All right. Understand how to do significant? Yes.
Since you had 10,000 kilograms, so that you gonna drop 3 zeros behind it, or you gonna keep it?
You don't drop them. They're just not significant. Okay. You see, this 0 is significant. Okay. These are not. They're still there because it's 500,000 or 10,000 or whatever, but they're still there because it's 10,000. It's just that what this means, what this means, that's not, it could be 9,980 kilograms. That would round to 10,000. It could be 10,100 kilograms. That would still round to that. Okay? It couldn't be 8,000. It could be 10,700. You know, it had to be something that it rounds to this digit. Okay? If you didn't have the bar there, let's just say to the nearest 10,000, to the nearest 1,000. That could be 9,000, 11,000, something like that. So this just says you're good to that many digits.
Okay.
After that, these are insignificant.
Okay, so
Yeah.
when you just delay 100, you made it.
Yeah. Right. That's the last digit that's significant. If it's a number, you just leave it as a number. But look to the right, and that can't have another number there except 0. So, yeah. All right. Good deal. Good question. All right. Get this back here. All right. And sorry about the interruption in the class there. Now, that was the A part. What is the kinetic energy of the driver as it strikes the plow? The B part here says, if the plow is driven 20 centimeters into the ground, so this is going to go from here to there is going to be 20.0 centimeters into the ground. Okay? That's how much is going into the ground. What force is applied to the plow? Now, I've erased the thing that we had, but it's the top of the page. If you got your books, page 216, that is 1/2 mv squared is equal to F times S. This is our S. Okay? We know what the 1/2 mv squared is. That's 500,000 joules. Okay? And we know the S is in centimeters. What's wrong with this picture? Our units. Meters, everywhere meters, but down here, centimeters. You got to get those centimeters into meters. Now, do you remember how to do that? 20.0 centimeters, you're going to multiply by blank blank to equal so many meters. What's the blank blank for? First blank for numbers, second blank for units. always put the units in their place. One unit's going to go on top and one on the bottom. You got a choice between meters and centimeters. One's on top and one's on bottom. What goes where? Meters on top. Very good. Putting centimeters on the bottom. Now you ask yourself, how many meters in a centimeter or how many centimeters in a meter? Either one you want to do. Anyone remember? How many centimeters in a meter? 100. You're right. Centi means 100. And which one is 100?
It's 100 centimeters in a meter.
100 centimeters in 1 meter. There, you've got a conversion factor. So you take this 20, divide by 100. Well, dividing by 100 is easy. That just moves the decimal 2 places to the left. And that makes it 0.200 meters. Okay? Anything zeros following a decimal, at the end of a number following a decimal, they're always significant. So you don't have to put a bar over those. That's 0.200 meters. Okay? So that gives us that F times 0.200 meters is equal to 500,000, sorry, I'm running out of room, joules. Okay? Well, let's hold off a minute. What is a joule? Break it down into smaller unit or different units.
Kilogram.
It's what?
Kilogram.
Okay, not that small. What's the next?
Newton meter.
Newton meters. I like it. Okay. Why? Because force is measured in newtons, and here we got meters right here. So that's going to be the most helpful. We could have gone to kilogram meter squared per second squared, but then you got to go back and fill in other things. So what we do here, and sorry about the uneven writing here, what we're looking for is the force from here, and we've got a displacement of 0.2, so let's divide by 0.200 meters. Divide this by 0.200 meters. The meters here go out, leaving us newtons, fantastic unit for force. Okay? Now, how do we do this division? Well, what I'm going to do is move this decimal 1 place to the right and make it a 2. That means I have to put another decimal here and move it to the right. Okay? And then this will be 2 into 5 will be 2 times with 1 left over. And 2 into 10 will be 5. And then a 0, a 0, a 0, a 0, and a 0. That's 2,500,000 newtons. We got a bunch of zeros there. How many of those are significant? Second? I can't hear. Did you say 2? I can't hear. Or 3? Okay. How many are significant? We've had 3 everywhere else, right? So let's do 1, 2, 3. That one's significant. None of the rest of them are. Okay?
And is
So
that because it's because of the 10 at the top?
because you had the 3 significance here, 3 significant here. This was 3 significant here. Everywhere you had 3 significant digits. So yes, that's why you count 3. The rest of them are there. They're placeholders. You got to have them there, but they're not significant. That 0 is, though. That means it could be 2,495,000. That would be okay. Or 2,540,000. That would round to that. Or 2 million. No, I'm sorry, I said it wrong. 2,504,000 would round to that, or 2,496,000 would round to that. So it's precise to the 3rd digit. Okay. Let's see how the book did. They put it in scientific notation. I was really tempted to put it in a bigger unit, smaller number. Does anyone know what 6 digits means? 2.50, you put the significant digit there, that's after a 0, you could call that meganewtons. Now you capitalize anything mega and beyond, so that's rather, it looks like Minnesota, but that's not Minnesota, that's meganewtons. Or the way the book did it, 2.50 times 10 to the, now here's what you do. You move your decimal 6 places to get this, so it's 10 to the 6 newtons. And that's how the book left it. 2.50 times 10 to the 6. You have to have your 3 digits there. Or I prefer 2.5 meganewtons. It's just that you may not recognize capital M, capital N as meganewtons. Okay. That was the B part of the question. Is there a C part? No. Okay. It says assume that all the kinetic energy of the driver is converted into work. Okay, so we've done it. How about example 3? Now we can't do example, or we could, but it's inconvenient. Let's go back to, let's see, what do I want to do? Okay. Go back to this one. All right, from current slide, and get my pen back. That's such a pain in the neck. Okay. A 60.0 gram bullet is fired from a gun with 3,150 joules of kinetic energy. Find its velocity. Yeah, was there a question?
I gotta go get my brother.
Got a what?
I gotta go get my brother.
Your what?
I gotta go get my brother.
Your brother. Oh, okay. Well, I'm recording, so it should be there. Yeah. All right. Okay, sorry, I don't hear well. Okay, so what we have is a gun here, and I don't draw guns well, so don't laugh and make fun of me. Okay, here's the gun. Here's the trigger assembly. Here's the stock. Here's the okay. There's your gun. You're laughing, aren't you? Okay, I see it. Okay, I'll remember that. Okay, all right. Here's the bullet. Now the problem is the bullet is only the mass of the bullet is 60.0 grams. 60.0 grams. It's fired from the gun with kinetic energy. I always want to put KE. They do E sub K. Kinetic energy of the bullet is 3,150 joules. 3,150 joules. Now, give you a hint here. I don't want joules as my unit. I want the smaller units. So this time give me what a joule is in the smallest units. Kilogram. Meter squared per second squared. Perfect. Those are the units I'm going to use. Okay? Now, what's wrong with this picture? Your joules are measured in kilograms. This is measured in grams. So we need to get our grams into kilograms. So how do we do that? Times blank blank equal blank kilograms. Got to go from grams to kilograms. What do we do first? Put the units into place, grams on the bottom, kilograms on top. Perfect. And then you match numbers with the units. How many kilograms in a gram or grams in a kilogram? Nope, that was centi. This is kilo. 1,000 which? 1,000 grams makes 1 kilogram. A kilo means 1,000. So 1,000 grams is 1 kilogram, 1,000 grams. Okay? So dividing by 1,000 means moving the decimal place 3 places. So this is going to make this mass 0.0600 kilograms. Okay? Now, lone zeros in front of a decimal are never significant. That's just to let you know the period coming there is a decimal point, not a period. Okay? Now, any zero before you get to the first significant digit, that's not significant either. But there's a significant digit, and then you have to have 3 after that because you had 3 significant digits here. So you have to put all 3 of those digits here. So that's 0.0. These two are not significant. These two are. 600. Any zeros at the end of a decimal number are significant. Okay. Now, what formula seems to be related here? We got, and what are we looking for, by the way? So what is the velocity? That's the unknown here. Velocity of the bullet. That's the question. Find its velocity, the bullet's velocity. So what formula relates those 3 together? E sub k is equal to 1/2 m v squared. Perfect. Now, you have 2 choices here. I call it plug and chug or chug and plug, whichever you prefer. You can either solve first for velocity, because that's what you're looking for, using just your letters. That's what I call chug and plug. Or you could put the numbers in that you know and then move your numbers around. Well, since numbers are bigger than the letters, I like to chug and plug. But you can do it either way you want to. Which way you want to do it?
Plug and chug.
You want to plug and chug, okay? Put the numbers in. You've got 3,150 in basic units, kilogram meter squared per second squared, is equal to 1/2 your mass, which is 0.0600 kilograms, times v squared. So now you got to solve for v squared. So what's the first thing you're going to do? You want to isolate the v. It's the first thing you're going to do. Give me an idea. Yeah. You can do that if you want to. That would be a perfectly good thing to do. You could have waited and done it too, either one.
Multiply the 1/2 by the 0.0600.
Okay, now that is a legitimate option. Multiply 1/2. In other words, divide 2 into 0.006. That'd be 0.0300. Okay? Excellent. 0.0300. If you had kept the kilogram, this is when you cancel them out. So you've already canceled them, so that's fine. Okay? Now you've got to, you divided both sides by 0.0300. Okay? So those go away. Yeah. Okay. So your v squared is equal to, now, got to do this division. Now, to do division, I like to move the decimal 2 places here, so I'm dividing by a whole number. So that means I have to move this decimal 2 places. Your calculator will do it for you if you're just using a calculator. If you're not, like I'm not, this is what I do. 3 will go into 3, 1 times. 3 will go into 1, 0 times. 3 will go into 15, 5 times. And then I've got 1, 2, 3 zeros, because I had to move this 2 places to the right. So 1, 2, 3 zeros. Okay. And my units are meter squared per second squared. And guess what, team? I don't want to know what v squared is. I want to know what v is. What's the velocity of the bullet, not the square of the velocity. So what do we got to do to get the velocity? How do you undo a square? Take a square root. So if you got the 105, I hope I did it right. Did y'all do it on your calculator? Second? Okay. So take a square root of that, and your v becomes, I can't do that in my head. I'm going to have to let y'all do it. It's going to be something like 300 and something. 3 what? 324. 324, but you take the square root of the units as well, that would be meters per second, which is a great unit for a velocity. So 324 meters per second. That bullet is moving really fast. 324 meters. That would be from one end of a football field to the other. That's the goal line to the back of the end zone and back again. Well, actually pretty close to end zone 3 times. Pretty close to that. That in 1 second. Okay, that's a fast bullet. Okay, so they got 324 meters per second. Good for them. Okay. All right. They do a little bit of talking here about another kind of potential energy, and that's called, it's if you had a coiled spring and you were either compressing it or stretching it, it's going to pull back at you in the opposite direction. Robert Hooke dealt with that, and as long as it's called an elastic activity, that means it always returns to its shape. Elasticity doesn't mean it will stretch. Elasticity means it returns to the original shape. It does have to stretch, but it returns to its original shape. I've had a few elastic bands that didn't before, okay? Then it's no longer elastic, okay? So, when it passes that, like you stretch it a little too far, anyone ever played around with a ballpoint pen spring, you get with it and start playing with it, and you probably shouldn't do that, but you stretch it just a little too far and it doesn't pop back, you've reached the elastic limit and it won't go back again, okay? So that's what we mean by that. The stretching the spring increases the internal potential energy of the spring. We call that either spring potential energy or elastic potential energy. But they don't do anything more about it, so I'm not either. So we get to the problem set 8.3. I would do either 1 or 3. Those answers are in the back. And any of the odds, 5 through 21, those answers should be in the back too. Okay? Any questions? All right, let's move on to 8.4. Now, we're going to go back to that slide we were on before. Guess we're through with that one. Ready for the second one? Okay. That goes there. All right. We're actually going back one slide to that one. Okay, from current slide. 8.4 is dealing with conservation of mechanical energy. Now, there is a definition, they sort of sneak in that very first line, and this is it. Let me write it for you in shorthand, but you can write it in longhand if you want to. Kinetic energy, E sub K, plus potential energy, E sub P, whether it's gravitational potential, spring potential, elastic potential, whatever kind, the sum of those two is equal to mechanical energy. And they probably are going to call it E sub M or E sub T for total energy. Okay? They usually use one of those terms. I like to call it mechanical energy because that's, I remember, ME, mechanical energy. These other things, harder to remember. So there is the foundation here. The sum of kinetic energy plus potential energy, that's called mechanical energy. And the law of conservation of mechanical energy says the sum of kinetic energy and potential energy in a system is constant if there's no resistive forces do work. Okay? So let me write that down for those who don't have a book. the sum of, which is exactly what I've got here, kinetic energy, okay, and potential energy, okay, in a system, okay, is constant if there's no resistive, if no resistive force does work. That's the law of conservation of mechanical energy, because the sum of these two is your mechanical energy. Other way to say this, mechanical energy is conserved as long as there's no external resistive forces, okay? Now, in the reality, there's always resistive forces, but if they're negligible, you can usually eliminate that, okay? Now, what was the formula for your E sub P? Say again? mgh, perfect. And what was the formula for your kinetic energy? 1/2 mv squared, perfect. Okay. Now, here's the deal, folks. If you remember what we talked about before.
When you raise the pile driver up H units above the pile, then you've given that much energy to it. That's potential energy, mgh. The mass of this times the acceleration due to gravity times this height. You've given it that much potential energy. Okay? Now up here, before you release it, what's its kinetic energy? It's just sitting there. What's its velocity? It's just sitting there. 0. So what is the kinetic energy? 0. Now when you drop it, and all this potential energy here converts to kinetic energy, it picks up speed the whole way down. Let me give you a hint. Halfway down, you've used up half of the potential energy, so the other half is kinetic. When it gets all the way down, all this potential energy up here, you see the kinetic energy up here is 0, potential energy is at its maximum, mgh. But right when it hits, and let's see if they have that on the slide. Yeah, right when it hits, the kinetic energy is at the maximum. Potential energy is 0 because you reach the 0 reference level. That's where the H goes to 0. So at the top, it's all potential energy. At the bottom, it's all kinetic energy. The sum of those two is the same, so that means the potential at the top equals the kinetic at the bottom. That gives us the formula, okay? And here's what it is. It's written at a couple of places in here, what they call maximum potential equal maximum kinetic. And the maximum potential is mgh, and that's equal to maximum kinetic 1/2 mv squared. Now, most of the time, we're looking for V. We usually know what the mass is. We always know what acceleration due to gravity is if you're on the surface of the Earth. We usually know what the initial height was. You can measure that. So we're looking for the velocity. Now, here's the interesting thing. Does the mass in this equation really matter? No, we could divide both sides by m and it just disappears. Okay? So that gives us, and then we can multiply both sides by 2 to wipe out the denominator. Okay? And then we could take the square root of both sides, and you have, where's my eraser? Okay. Take the square root of both sides. I'm going to switch sides at the same time.
V is equal to the square root of 2GH. And that's the next formula you have there. Your velocity at the bottom, right as it hits, is the square root of 2GH. The mass doesn't matter. I mean, the mass is providing energy, but the velocity depends only on the acceleration due to gravity and how far it fell. That's all it depends on. Okay? And the acceleration due to gravity is what? Two different numbers depending on what units you're in, what system you're in. It's what? 9.80 if you're in meters per second squared, or 32.2 if you're in feet per second squared, U.S. customary. Okay. And H is the height above the reference level when you first dropped it. So let's move on to example 1. A pile driver falls freely from a height of 3.50 meters above the pile. So I think I'll go back to the previous slide. And this height is 3.50 meters above the pile. Okay. What is its velocity as it hits the pile? We're looking for V. Can anyone tell me how to get that? Say that one more time.
Velocity.
Yeah, that's velocity. What are we looking for? That's what we're looking for. Square root of 2GH. Let's use the square root of 2 times. Yeah, since we're in meters here, we use the meter per second squared. So that would be 9.80 meters per second squared times your height. And what's your height? 3.50 meters. Okay? So this will be the square root of, oh boy, well, 2 times 3.50 would be 7, and 7 times 9.8 is going to be something about 6.9 something, 6.8 something. No, 60 or 68. Okay, say again. 68.6. Okay, now did you round any or just leave it? Okay, good. 68.8 meters squared per second squared. Okay? And when you take our square root of that, that's going to be something just a little bit more than 8.
8.28.
28. Okay. 285?
2825.
25. Okay. And that would be, take the square of the units too, you get meters per second. Okay. Now you got too many digits there. How many do we need? 3. 1, 2, 3. Look to the right. That's a 2. It's an ugly 2, but it's a 2. So what happens to it? You drop it. So that would be 8.28 meters per second. Why do you drop it rather than put zeros in? Because you're to the right of the decimal point. If you put zeros in there, they become significant. You just drop them anything to the right of a decimal point. If you're left of a decimal point, you have to keep your zeros in place. Yeah. So that's 8.28 meters per second. It's going pretty fast for something that heavy. Well, they didn't tell us how heavy it was. Doesn't matter. Okay. 8.28 meters per second. Good deal. Any questions on that?
You don't erase it. How can you mentally do it first? In the book, there's the break to do it like you just did.
Yeah, in the book, they just put the conversion factor and act like you know what to do with it. You know, to me, if you use the train track method, all you have to do is put the units in the place so they cancel out properly, match the numbers with units, and it takes care of itself. You don't have to memorize anything except how many meters are in a centimeter or whatever. All right, now there's another use of conservation of mechanical energy, and that's with a pendulum. And here's what we mean by a pendulum. Now, this is a bit exaggerated, but we'll go with it. A pendulum is a mass of something hanging from a pivot point, okay? And the thing it's hanging on is negligible mass, very little mass. We count all the mass as being in the ball at the end, okay? Now, if you need something to think of, y'all know what grandfather clock is? Yeah, you know, it has that thing swings back and forth. That's a pendulum. If you've ever been to the McWane Science Center, at least many years ago, had a huge pendulum that hung from the roof. I've heard from students now that it's not there anymore. Probably took a bit of effort to maintain that, so they probably took it down. But here's a pendulum, okay? Now, what they're showing here is that when you raise the pendulum up to a certain height, okay, they say 65 degrees. Now, that's a bit much for a pendulum, okay? But we'll use this for it. When you raise it up this high, you see, if you had let this be down here, it would be down here somewhere, right? That's going to be your zero reference level. That's as low as this pendulum will go when you release it. So that's your zero reference level, whatever height that is off the floor. Okay, but you raise it here. What's its kinetic energy there? You're holding it right here. What's the kinetic energy? Zero, because its velocity is zero. It's not moving. You're holding it there. Okay? Now, when you release it, it falls, right? So it starts, and so here it has maximum potential energy, depending on how high this is above the zero reference level. MGH. Okay? Zero potential energy here. Now, when you release it, it starts falling. Okay? And as it falls, it's losing its potential energy, but picking up kinetic energy. It's increasing its speed, isn't it? Okay? And where's it going to reach its maximum speed? Right there. Because what's it going to do when it goes past there? It starts going up again. So it starts losing speed. So it's going to increase speed till it gets here, reaching maximum kinetic energy. And then it'll start increasing height again, which slows it down and increases potential energy. How high will it go? It'll go 65 degrees over here. As long as there's no friction here and no air resistance here. Now, there's always a little bit of friction and a little bit of air resistance, and that's why you have to wind a grandfather's clock to overcome that. But if it had perfect rate, but now what else about true about a grandfather's clock? Have you ever noticed it? Big old pendulum is about that big, right? How thick is it? Very, very thin. So it goes this way, so it has very little air resistance. What else? It's usually enclosed in a glass case. So there's no wind to blow on it. Okay? So it minimizes the air resistance. Now there's always a little bit of friction up here, and you can tell that because it goes anything that makes sound that has to come from friction. Okay. So, but if it was a perfect world, perfectly lubricated here, no air resistance here, very thin, then it would come up to 65. It would have to stop. Why couldn't it go any higher? Mechanical energy is conserved. If it went any higher, it would have more mechanical energy there than it did here, and it can't. Mechanical energy is conserved. It's always constant. And the sum of kinetic energy plus potential energy is mechanical energy. Now, how could it go further? Notice I said you release it here. What if you threw it? Now it could, because you've given it an initial velocity, so now it has kinetic energy here. If you push it and give it velocity, then it has kinetic energy here, so over here it might go higher, and it would, because you gave it more, you gave it some kinetic energy here, so when it gets over here it stops. The E sub P is greater because it's the sum over here. The kinetic energy would be zero where it stops. But we don't do that. We just release it. Okay? Now, what I've just been waving my arms about, the next slide shows it. Okay? Now, they tried to say this is exactly halfway between these two positions. And if it is, then at this point, you got half of your potential energy became kinetic energy. So your potential energy is half what it was before, and your kinetic energy is increased, so now it's half and half. Okay? You let it go on down further, and now it can't go any lower, so potential energy is zero. You're at your zero reference level. But now it's all kinetic energy. This is as fast as that pendulum will ever be going. Okay? So that's all your mechanical energy is now in the form of kinetic. Up here it was all potential, no kinetic. Here it was half and half. Here it's all kinetic with no potential. And it goes through the cycle again, going up here to half and half, and up here till it's all potential and no kinetic, because it stops right there. Does that make sense? All right. That's a pendulum. Conservation of mechanical energy. So let's see. Example 2, that's what is 8.3? Yeah, 8.4. Example 2 in 8.4, drop a 5 kilogram mass. Oh, they don't do any problems with pendula. Shame. But they do this one. Now this is, frankly, a pain in the neck problem. Okay? So I'm going to have to go back to the other slides so we can do it there. And we're not going to do them all, I promise you. Okay? All right. It says drop a 5 kilogram mass. And when they say a 5 kilogram mass, let me get my pen back. The mass of this object that you're dropping is 5.000005 significant, no, I'm sorry, I put one too many. Okay, sorry about that. 4 significant digits. We haven't had any with 4 before, I don't recall. Mass from a hot air balloon, and this hot air balloon is 400 meters above the ground. So that looks like that's going to be our H is going to be 400.0 meters. This is kilograms. I forgot to put my units in. Shame. Okay. Now, as soon as you have that decimal 0 there, that makes this one significant, so that makes it 4 significant digits. You don't need to put a bar on it because that last digit is past the 0. Okay. So there you have that. Find the kinetic energy, potential energy, the sum of the kinetic energy and potential energy, which, by the way, is mechanical energy, and in 1 second intervals until it hits the ground. Are you kidding me? Okay. That's what they want you to do. Now, so what we have is the ground down here. Okay. We have a hot air balloon up here. You're in the basket here, and you're dropping out of here a 5 kilogram mass. Okay, and you are 400 meters above the ground. That's your H. Your initial H. I'll put H sub I, because you're going to have bunches of H's here. All right. And they want you to do this for every second that it falls. And they tell you in the table that's going to be about 9 seconds, a little over 9 seconds. So your first column here is the time in seconds, and it's going to be 1. Well, okay, they're going to start with 0.00 seconds, 1.000 seconds, 2.000 seconds, 3.000 seconds, 4.000 seconds. Are we going to do all these? I hope not. 5.000 seconds, 6.000 seconds, 7.000 seconds, 8.00, I don't have room to write them all in here. It goes up to 9 point something another. We're not going to get that many. Okay, we're going to stop way before that. All right, that's your first column. The second column is your height in meters that you dropped it. Now, I called it H here. They're calling it S. Okay, whichever you want to call it. The height that you... Now, you're dropping it at 0 seconds, so that's going to be, oh, I'm sorry. No, I said it wrong. S is the distance that it's fallen here from the basket. This is still your height here. S is the distance that it's fallen in so many seconds. So at 0 second, it hasn't fallen yet. You haven't released it yet. So at 0 point. Now, here's the weird part. They only put 2 significant digits here. Now, I can't tell you why they're doing it this way. It's bizarre, okay? You're not, it is, okay? All right. Good deal.
Thank you. Thank you.
All right.
We'll talk. I see your email.
What's that?
I said we'll talk. I see your email.
Okay.
Okay. Thank you, Doc.
All right, glad to.
Have a good evening.
All right. Okay. Now, we'll hold off the rest of those. Then they say what is the third column is the velocity in meters per second. Okay? We'll talk about how to do that. At the beginning, it's 0.00. Now, why the 3 digits there? I don't know. Now, next will be E sub k, kinetic energy. If it's 0 velocity, this is 0. Now, this is measured in joules, by the way. Okay? Now, the next one is H. That is how high it is above the ground, so that is in meters also. But this is height above the ground, and that will be 400 to begin with. Okay? 400 to begin with. Then after we know that, we can calculate E sub P, potential energy. That will also be in joules. Okay? And then we'll do the total energy, which I like to call mechanical energy. They call it total. I call it E sub M, mechanical energy. And that will be in joules. Okay. So that's what we're going to do. I'm going to erase some of the stuff that's in the way now. Like that, and that, and that, and that, and that, and that, and that. Okay. In fact, I've just may move my whole balloon and everything else over here. Okay. Can't get my pen to work. There it goes. Okay, here's the balloon. Here's the basket. Here's the mass, 5.000 kilograms, wasn't it? That's not in the table anywhere. Yeah. Okay. And your height that you've fallen, that's your S. And the height above ground, that's your H. And the initial H sub I, is equal to 400 meters. 400.0 meters. Okay. Now, I filled in what we had so far. We didn't calculate E sub P. What is that going to be? What's the formula for E sub P? Potential energy. mgh. Your M was 5 kilograms. Your G is 9.8 because you're in SI units, 9.80. And your H is 400 meters. So if someone's got a calculator, 5 times 400 would be 2,000. and multiply that by 9.8, you got about 19,000 something another. 19,600. 19,600 joules. Now, where's your significance there? I'm guessing it's that first zero. Yes, that's what they put it as, first zero. What's your total energy? Which is the sum of kinetic and potential. Kinetic was 0, potential is 19.6. What's this? 19.6. And that's also joules. Okay. They're leaving the units off because they put the units at the top, so I'll do that too, just to keep from having to write something else. I have it at the top. Okay. Now, we go down 1 second. How far does it fall in a second? Ooh. Do you remember the formula for that one? S is equal to 1/2 gt squared. Remember that? How far did it fall if it accelerated at g? That was one. This was from chapter 5, way back. That was your formula. Well, g is 9.8, t is 1, and 1 squared is 1. Half of 1 is 1/2, and 1/2 of 9.8 is 4.9 meters. Oops, they're not putting the units in. So 4.9. See how they got that? Okay. Now, what is velocity after 1 second? Well, if you think about, it says it's 9, what your acceleration due to gravity is, 9.80 meters per second per second. Meters per second squared. So that means it would be 9.80 meters per second. Because in 1 second, it would pick up speed that much. Now, what is its kinetic energy? What's the formula for kinetic energy? Help me. Kinetic energy formula. 1/2 mv squared. Okay? So your m is 5.000 kilograms. So 1/2 of that would be 2.5 kilograms. Multiply that by 9.8 squared. So 2.5 times 9.8 squared. See what you get. Say again? 630, is that what you said? 240. Okay, sorry, I can't hear. 240. 240 joules. Okay? Now, if you fell 4.9 meters, that meant, and you were originally at 400 meters, that means you're at 395.1 meters. Right? Subtract 4.9 from 400. So if you're at a height of 395.1 meters, what is your potential energy? It's your mass, 5, times g, which is 9.8, times your height is now 395.1. So someone punched those numbers in. 5 times 9.8 times 395.1. Okay, 19,360. Okay. Now here's a good check, folks. What is your kinetic energy plus your potential energy? 240 plus 19,360. 19,600. Isn't it? Yes, it is. So that's working out well. All right, let's go back to 2 seconds. What is your height, the distance you've fallen? 1/2 g times 2 squared. So that's 1/2, 9.8, so that would be 4.9 times 4. So 4.9 times 4. 19.6. Anyone do it? Is that right? So that's how far you've fallen. What is your velocity now? Well, that's, you increase your velocity 9.8 meters per second every second. So you double this, and that would be 19.60. Okay? What is your kinetic energy? 1/2 the mass, that would be 2.5 times this velocity, 19.6 squared. Anyone do that? That's 2.5 times 9.8, no, I'm sorry, times, well, 19.6 squared. 960 joules. Okay? What is your height now above the ground? If you've fallen 19.6 from 400, that would be 380.4. Okay? Because the sum of those have to be 400. All right. What's your potential energy? M, which is 5 times 9.8 times 380.4. Say again? You say 18 something? 18,530? Is that what you said?
640.
640. Okay. And then as a check, add that to 960. And what do you get? 19,600. Yes. All right. You see how this works? You want to do them all?
No.
Please, let's not. Okay. But you see how it works. And it really is a pretty good exercise in doing everything we've done. How far it fell, that was from Chapter 5. The velocity, that was also from Chapter 5. The kinetic energy, that's from this chapter. H, you subtract how far it fell from 400. Potential energy, mgh, that was from this chapter. Add them together and you get total energy. That should not change. Mechanical energy should be constant. Very good, folks. You can keep on going and do the whole table if you'd like. Okay. Or not. Okay. So if you're okay with it, we'll discard that. All right. Thank you so much. Let's move on. Now we'll get to that slide we've seen a couple of times here, and that is the work done by a roller coaster. Okay? Oh, my goodness gracious. Where is the greatest potential energy of this roller coaster? Up there at P. Okay? Now, I don't know exactly how roller coasters work, but I believe what they do, they have some sort of chain mechanism on it, and some motor is pulling you up until you get to that point. And at that point, they let you go. Well, you're at zero kinetic energy here, or just about, and then as you start falling, you start losing that potential energy here and gaining kinetic energy as you go, and you reach your maximum kinetic when you get down here, and you go back up, and as long as you don't have anything higher on this side than you did here, it will take you and zoom you and twist you and turn you, and here, and this is where you probably get off, new group get on, They pull you up to here, and then you go back again. Okay? It's all conservation of mechanical energy. Losing potential energy, gaining kinetic energy, losing kinetic energy, gaining potential energy as you go back up. Back and forth, back and forth. Is there ever no friction? No, you always are going, you know, if you hear noise, there's got to be some friction. Don't pay attention to the screaming. That's another issue, okay? But that's not losing energy. Your reference level is as low as you can go, and that's what they show there. All right. There is a blurb here on backyard physics, and they show a croquet set. Have any of you ever played croquet? That is such an old game. I can remember when I was a very young kid playing it a little bit. Never was any good at it. But anyway, we have a croquet set in our garage that my wife got just in case nieces and nephews ever wanted to play it. They never have. So, all right. There's another physics connection that's landing on an aircraft carrier. And I was on an aircraft carrier, and I've watched them do this. What they do there, an aircraft carrier is pretty short. I mean, it's about maybe 2 or 3 football fields. No, not that much. A little over a football field in length. But that's going to have to launch the planes and take off. You know, no, you're not going to do a jet in that unless you do something to stop it. And to land on an aircraft carrier, they have these tension cables across the deck, and they have a hook on the bottom of the plane. When they come in, the hook catches them, and it yanks them to a stop. Okay? They're talking about that. It's a way of increasing potential energy in a big hurry. And the picture on the next page shows that. All right, homework exercises here in 8.4. Do any of the odds 1 through 13. Most of those answers should be in the back of the book. If they're not, don't worry with them. All right. Now, 8.5 really has absolutely no, it just talks about alternative energy sources. It's all good stuff. Read it, enjoy it, but there's no problems in it. Basically what you're doing, you're getting energy from other sources. Hydroelectric energy, let water build up behind a dam. What's that doing? Increasing its potential energy. Then you let it through the slough. It goes rushing down, picking up potential kinetic energy, and the kinetic energy is used to turn the turbines. The turbines produce electricity. Clean energy. Okay? Windmill does almost the same thing. The wind energy is caught by the turbines. They're turning and they're producing the electricity. Okay? Again, clean energy. Geothermal energy takes heat off of very hot lava rock, bring that to a boil, and produces steam, catch the steam, run it through a turbine. Again, you're not expending any fossil fuels. Solar energy catches light from the sun and converts that through a thing called photoelectric effects into electrical energy. That's DC, direct current, not AC, so you have to convert that, but it's still clean energy. There's another blurb there on wind energy on the bottom of page 226. That's worth a read. And wind turbine technician, I don't know why they put that in there, but it looks pretty interesting to me. There's a glossary. There's some review questions. The formulas there that we've hit every one of them. Review questions help you understand the concepts. Review problems. At least the odd numbers have the answers in the back, so you could do any of the odds 1 through 15. All right, that's all you have to do. And the trouble is, unless Dr. Marable is still here, I didn't know we were going to finish tonight. I don't have the copies made. I'm going to see if I can get in the, all right, here comes some tests. Good deal. Let me see if I can get into the office and make copies for the second test for you. Oh, someone bring hers up here. She's limping like a pathetic, no, I'm just kidding. Okay, it's really hurting, huh? Sorry. All right, everybody got it in. Let me see if I can find some way to get in the office. Okay. What's that? If I can get in the office, I'm going to pass it out today. How many did we have? I think we had 9 here. I think a total of, 11? We're missing 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. Let me see if I can get 11 run off real quickly. If anyone's still here, I doubt if they are.
I'm bad at math, so this is just like, oh my god, I thought I was done with math. And I was like, I don't understand it. It's like the formulas and then the units and all that confusing me so much. It's really confusing. Yeah. I was like, well, and then I got to do the ACT. You gotta make me say understand.
I got a key so I can get things off.
And next semester, I'm just taking medical terminology. I'm gonna have to take 4 more.
You need to take it back. So.
Yeah.
You take it online?
I have to be in the classroom.
But see, online, you see your class is better than other lady teachers. She's not like the lady. So she told me the girl is another girl taking it on the class. She said, I'm not no problem.
If I
Even
can
if
take
it's
classes,
just like this.
I can take it by itself. I don't know what's in my class. I'm taking that. I got it out the way. I can't wait till I say that. But I made like a 74 on the good air, but I like both tracks. She gave me extra points for perfect attendance. And I brought it up to 84, and I was like, oh, that's good. I think that. That's good.
Thanks for hanging. Now this one may be one of the only tests that is that I don't think there's any errors on the test, but let me just check and see real quickly here.
Me too. I have no time to study for my job and
I think it's all good. Okay, so work on it this week. I'm still recording. I meant to pause this, but I passed out the test, so if any of you aren't here, you can try to get it from me sometime this week so you can look at it and start working on it. If you run into problems, there'll be good things to do, clear up next week. Now, remember, I won't work a problem. I will try to explain a problem, but I won't work it. If you find anything in the book that's similar to what's on the test, I'll work anything in the book. Okay. All right, so I'm going to end this. I'm cheating you out